Are you just gonna put out like a number or something?
I might. I'm gonna try to figure it out. Hit that little. Well, you probably know how to operate that.
What?
button.
No, I don't.
The pause. Hit the pause button when I start going here.
All right, so last unit we have the ability to self-ionize. What that means is that when you take water and you dump it into water, it doesn't just stay water molecules. Actually, some of it makes this hydronium ion, the H3O plus ion, and some of it makes the hydroxide ion, the OH minus ion. Okay? And since water has the ability to do this on its own, that means that in every single bucket of water, there is some of this floating around, and there is some of this floating around. And as a result of that, when the equation is balanced as it's written here, the H3O plus must equal OH minus. Now, this is in brackets here and here, and this is in brackets here and here. And a little chemistry notation says that anything that's in brackets, we call that concentrated. Or so this is telling you the concentration of hydroxide versus the concentration of the hydronium ion. And so what that also allows me to understand is that a lot of times H3O plus is associated with things that we call acids. And a lot of times OH minus is associated with things that we call bases. Right? And so the issue is that if we are able to identify that water self-ionizes, some of water is going to form some acid qualities and some of water is going to form some base qualities. At 25 degrees Celsius though, when this happens, the amount of H3O plus that's found in a bucket of water is equal to 1.0 times 10 to the minus 7 moles, or is molar rather. Whereas the amount of OH that's found in a bucket of water is 1.0 times 10 to the minus 7 molar as well. So when these two things are equal, we have basically pure water. The ionization constant of water allows us to do some work with these two values. The term constant in science, right, means never changing, right? Like the constant for the speed of light is like 3.0 times 10 to the 8 meters per second. That never changes. That's just something that we as scientists have expected and used. The ionization constant of water, though, is called Kw. And Kw is equal to the concentration of hydronium ion times the concentration of hydroxide ion. And so in this instance, the Kw is equal to 1.0 times 10 to the minus 7 from the last slide, times 1.0 times 10 to the minus 7 from the last slide. And that gives us a value of Kw to always be 1.0 times 10 to the minus 14. That's going to be important in a few minutes. So Kw always equals this value. And if this is always the value for Kw, it would be great if H3O plus was always 1 times 10 to the minus 7 and OH was 1 times 10 to the minus 7, but that's not usually the case. What is usually the case is H3O plus goes up and then OH goes down inversely. Or H3O plus goes down and then OH goes up inversely. And what that allows us to know is that if a solution has H3O plus equal to OH minus, then it's considered neutral. If a solution has more H3O plus than OH minus, the solution is considered acidic. If the solution has less H3O plus than OH minus, then the solution is considered basic. And I promise you, on a test, I'm going to ask at least 1 or 2 questions that I give you one of these relationships, and you have to tell me if it's acidic, basic, or neutral. So you need to understand this relationship.
Will it be in an equation?
Maybe. Or it might just say, given the following, is the solution acidic, basic, or neutral? Okay? Now, some other things that we have to understand. In our class for chemistry, we are going to only work with strong acids and strong bases. And when we work with strong acids and strong bases, we now know that we can make some assumptions. And those assumptions make the math a lot easier. And so in a situation like this, a problem that says a 1.0 times 10 to the minus 4 molar solution of HNO3 has been prepared, and I ask you to calculate H3O plus and OH minus, okay, you get to make 2 assumptions. If you have an acid, you get to know automatically the H3O plus concentration. If you happen to have a base, you get to know the OH minus concentration. And since this happens to be an acid, and we know the molarity of the acid, we get to know the concentration of the H3O plus based on this assumption. So the formula that we're going to use to do this calculation is the KW formula. Which looks like that. That was the formula from the other slide a couple slides ago. So in this case here, KW we have to work with some of the things that we know. We always know KW, and KW is always going to be 1.0 times 10 to the minus 14. Okay? Because this is an acid, and I know the concentration of the acid, I know that H3O plus is 1.0 times 10 to the minus 4. Okay? And so, as a result of that, I'm asked to calculate OH minus. So I can just go ahead and substitute So I can go ahead and substitute into the KW formula. And when I substitute into the KW formula, I can now solve for OH minus by dividing both sides when I divide this out, I get a value of a concentration of 1.0 times 10 to the minus 4, minus 10. Now, to go back to the fact that this is an acid, as we were given before, H3O plus, OH minus, which one's bigger? H3O plus or OH minus in this case? Hard? H3O plus is bigger. This is 0.0001. This is like 0.90 in a 1. So this one is significantly larger. So our data or our math suggests that this is definitely an acid. You follow that so far? Another example would be this guy right here. Determine hydronium and hydroxide ion concentration for a solution that's 3.0 times 10 to the minus 2 molar. So we're going to use the KW formula. Here. Now, we know that KW is always that. What type of a solution is sodium hydroxide? Is it an acid or is it a base? It's a base. How do we know it's a base? It has hydroxide in it. And because it's a base, we get to automatically know the concentration of OH minus. And so in this case, the concentration of OH minus is equal to the base's molarity, is equal to that. Okay? So now I'm going to go ahead and calculate the H3O plus, which allows me to use the KW formula. Which is that. And so when I divide both sides by the 3.0 times 10 to the minus 2 molar, I get a value for H3O plus . 3.13 times 10 to the minus 13. So again, if this is a base, which one is bigger, the hydronium ion or the hydroxide, or the hydronium or the hydroxide ion? hydronium is 0.03. This is 0.1203. So which one's bigger? The hydroxide is bigger, so that tells me that this is a base. Okay? Now, yesterday, as people were